Yes, Nisha. Start it.
Okay, yeah. Very good afternoon, everyone. Thank you for joining us for this sixth webinar of Teaching the Next Gen webinar series. Today, we have with us Sugat Dabolkar, who is going to conduct a webinar on computational thinking. Sugat is a doctoral researcher in the Learning Sciences program at Northwestern University. His work involves designing technology enhanced learning environments for learning scientific thinking, computational thinking, and complex systems thinking. Over the past several years, Sugat has developed many computational agent based models, most of which have been incorporated into high school science curricula. The curricular units that he has authored and co authored have been used in schools in the US as well as in India. He has presented his work in several highly prestigious international conferences and has co authored several peer reviewed journal publications. Prior to starting his PhD in educational research, Sugat was first a computational biology researcher and then a science content developer for multinational organization in India. Sugat has been associated with our group at IISER. In collaboration with COSME at IISER Pune, Sugat worked with high school science and mathematics teachers around Pune district. They co-designed high school science and mathematics school units or school curricular units that got incorporated into computational models to engage students in scientific inquiry practices in disciplinary contexts. It was really a pleasure to collaborate with Sugat, let me add that. And I was fortunate to be around when Sugat conducted his workshop here. Um, I could see that he works very closely and he has a very hands-on approach with teacher training. He helped them in every single step, and I could see the teachers' beliefs transform through the workshop, wherein they were first doubtful whether they can really do this computational thinking and scientific inquiry as a regular practice in their classroom, and slowly they became very confident and became the masters of this technique. So I was very glad that I could witness it firsthand. And I'm sure that all the teachers that were a part of this workshop would have told you that they thoroughly loved being part of this workshop based on their feedbacks. So today, I'm sure that you will all hear about this series as well as many other experiences that Sugat has, that he has gathered from working with teachers around the globe. So I request Sugat to start his webinar.
Thank you. Thank you, Neeraja, for the kind introduction. And yeah, first of all, let me thank Neeraja and Bhakti, the organizers of this web series, for inviting me. And I'm happy and I'm excited to conduct this session with Asim and Prachi. So let me start sharing my slides. So this talk is going to be about using computational models to teach scientific inquiry in a classroom context. And I'm going to start a little bit talking more about myself before I get into the talk. And this is somewhat additional part than the introduction. So I grew up in this beautiful hilly town, Satara, which is in Western Maharashtra. And I spent my first 16, 17 years of my life till my 12th standard there studying in a Marathi medium school. Then I did my BSc in Pune, MSc in Bangalore, MBA in Jamshedpur. After that, I worked in Mumbai and Chennai 2 years each. The reason for telling you all this is that I have been all over India, kind of, and I want to connect this talk to everyone in a way that they can incorporate this in their teaching. I was fortunate enough to have amazing science and mathematics and other teachers in my school in Satara and during my educational journey afterwards. Currently, I'm doing PhD in Chicago, a suburb of Chicago, at Northwestern University. So from one beautiful place in India to another beautiful place in the US. And my research and design focuses on how people learn. So currently I'm doing research about student learning in classrooms and how can we design to support this learning. So my focus is on both research and design. In this talk, I want to discuss the following aspects. So I know many of you in the audience have attended last week's webinar series talk about scientific inquiry. So many of you know how a scientific inquiry can be approached in classroom context. I'm going to talk a little bit about that. I'm going to start with why do we need to teach scientific inquiry. Then I will talk about using computational models to teach scientific inquiry. And this has become even more important in current context when a lot of teaching has to be done remotely. So I'll discuss some theoretical aspects and pedagogical aspects of this, and then we will perform a demonstration. So we will have a classroom scenario for you where Asim and Prachi will enact as students, and this is not highly structured demonstration. So it is something that we want you to get a sense of how such models and learning plays out in a classroom setting. And finally, we will discuss how we can use computational tools. So models in particular, but tools in general to support students become active inquirers. And this part is important, that they have to be active in the process of learning. Okay, so why teach scientific inquiry? And it's an important question. So let's think about learning in different contexts, and especially the context in Indian setting. So these are two sports people. You might recognize them. And when we want students to learn sports, what we ask them to do? We ask them to play, right? And they're not reading books how to play a straight drive or cover drive. Some of them might, but it's important to go on the ground and start playing. Music. When we want students to learn music, we want them to play, right? And the last two pictures are of people who you may not recognize, but these are two eminent scientists in India, Ashok Sen and Satyajit Mayer. And when we teach science, why are students doing something that is different than scientists do, right? We tell them, okay, this is how Newton's laws are, or this is how pressure or temperature works with gas molecules, or this is how evolution works, and so on and so forth. But why can't we let them play a sport or a music, just like they play sport or music? Why can't we let them play science? So can they actually play with science and learn as active inquirers of science? And when we think about scientific inquiry, this is next generation science standards in the United States, and they have come up with this list of 8 practices. Okay, so scientific inquiry is not just one method of you do A, then you do B, then you do C, and then you do D, and then you are a scientific inquirer. It's not like that. Scientists, when they engage in scientific thinking uh, and scientific temperament in their regular work, it's not a very linear process. So they ask questions, they develop and use models, they perform investigations, collect data, they engage in mathematical and computational thinking to build explanations, get into arguments, structured arguments based on evidence, and evaluating and communicating information. So these are practices that we want our students to learn. And the practice in the center, which is slightly bolder and bigger in size, is computational thinking, which is becoming more and more central to current scientists. And this is something that you are becoming more and more familiar with. The National Education Framework, the NEP that's been released this year. And it also aligns with this idea, right? So there is emphasis on conceptual understanding. So students should not be doing rote learning and learning for exams, but they should really understand the concepts. We need to identify unique capabilities of students and encourage them. So role of teacher is not just to tell things, but identify these capabilities and allow students to develop those more critical thinking and creativity. So this is a central part of scientific inquiry, that we want students to engage in critical thinking. And in today's talk, I'm going to talk about how technology can be used for this. So we are going to think about this in the context of our classroom education. Okay, so this work that I'm doing is based on the research that I have been performing over past for more than 4 years. And it is about developing technological tools that will allow students to collectively build knowledge. Okay, so if you see this little diagram on the right side of this slide, what do scientists do? So there are scientists in India, in the US, in Japan, in Afghanistan, and they collaborate. They each of them work on different aspects of a phenomena. They write research papers, they share information, and then they collectively build knowledge about theory of evolution or quantum dynamics or artificial intelligence. So just like that, can students in a classroom setting engage in this? So earlier I showed you that slide, that what professionals in the field are doing, we should let students play with those ideas, right? So can we do that? Can we create that kind of learning environment in our classroom so that they can collaboratively build knowledge about different natural phenomena? So how does it look like in the classroom? What should be the pedagogy? What should be teaching strategies when we are using computational models as microworlds? So this is a new word, microworld. So the computational models that I'm talking about are designed, and we will give you a demonstration later on. So these models are designed so that students can interact with those models, and those models have representation of real world phenomena. So these are like micro worlds in which students can engage in conducting their own explorations, their own investigations. So they start exploring these models. On the right side, you see these students sitting on their laptops. And now it is because of the pandemic, more and more students have started working on their laptops or phones or tablets, different computational tools. So So they start with exploring these models. They start playing with those models. They start making observations, what's going on. They change certain things. And then they perform scientific investigations using those models. And then they share it with the classroom. So this is a student in the classroom who's sharing his data and his observations. And finally, they reflect on this process of both the, the conceptual understanding of the phenomena as well as the process, how they figured it out, right? So when we teach this in a classroom setting, what should be role of a teacher? Teachers should be facilitating this process to actively engage students in constructing computational artifacts to build knowledge. And some of these things will become clear when we do the demonstration of this. But what I'm talking about here is students should not be passive listeners. When you're using these models in classroom, you should not be showing students, okay, this is how it's done, look at this and learn. What is important and what is possible with the computational technology these days is that they can interact with these models on their computers. So they become active participants for constructing the knowledge. And then they can take screenshots, they can record their observations using innovative ways, see what's going on, try to collect data and build knowledge collectively. So they can come up with a research question. They can design and perform scientific investigations, and then they can share research findings with each other, right? And as a teacher, you can facilitate this process. So this all sounds great, but now we have been thrown another big challenge, the pandemic, and many of you, almost all of you, are teaching remotely, and that also creates both challenge and opportunity. I mean, having this kind of webinar series, I'm sitting early morning in the United States, in some town, and talking to you all. You are listening from different parts in India, in the world, and this wasn't very common before the pandemic. Students have more access to technology, but teaching remotely has become important. So it's you are undergoing these challenges, and it's not easy. Every day there is new challenge, and you have to figure it out. You are concerned, are my students really listening? When I start teaching, what are they doing? Because in classroom, I can see their faces. Some of you ask them to turn on their cameras, but not sometimes students don't, and you can't really keep on monitoring that. You want to know what are they doing sitting at home? Are they really are they learning, and what are they learning? And you want to get a good sense of that. So we're going to see how we can do it effectively by actively engaging students in the process of learning, relating their interests and their prior knowledge. So in order for students to engage in this process of learning, whatever they're learning, if it connects with their own interests and their own idea, even for us, right? When we learn something new, if we can relate to it, we are more interested. Project-based learning, asking students to produce concrete projects, concrete artifacts, something concrete where they're actively building these, and these can be computational artifacts. So this is something that we'll see, and creating a cohesive learning community. So they should be learning from each other, and that is become more difficult when it's online. But they have been doing that, and they are smart. They even talk to each other. even during, they find innovative ways to communicate about not science and math and study things, but they can also do that. So building this cohesive learning community of students where they can share and there is a lot of peer learning is something that can potentially be done when you're teaching remotely. So can we use computational models to do all this? And so this is something that we are going to demonstrate and have discussion about in today's class, today's talk. Yeah. So how can we do all this using computational models? So we're going to conduct a virtual demo with Asim and Prachi. So Asim and Prachi, can you start sharing your screen? Hi, Asim.
Hi.
Hi.
And Prachi. Okay, let me change my Zoom settings so that I can see you also.
Yes,
Okay, great.
while Sugat is doing that, let me quickly introduce Asim and Prachi. I realized that I forgot to introduce them at the beginning. Both Asim and Prachi are my colleagues here at IISER Pune, and they're both senior teaching associates. And Prachi has a major in physics, and Asim is a major in biology. So, thank you, Asim and Prachi, for joining us today.
Yes. Thank you,
Okay,
Neeraja.
okay. Okay, Asim, you don't have to share your screen. That's okay.
Okay.
For now. Okay, great. Thank you. So for next 40 minutes, we are going to, or 30 minutes, we are going to simulate a classroom situation. So in this situation, I'm going to be a teacher, and Prachi and Asim are going to be students, and they are going to use a computational model to learn about something. So I have already assigned them a computational model using a website, which I will talk to you about later. So can you open the lesson that I have shared with you, Prachi and Asim?
Sure.
Yes.
And once you open the lesson, you will see um, something which I'm seeing on my screen. So this is what you should be seeing on your screen.
Yes.
Yes,
So
If
yes.
it
we can see that this is the page
okay,
0. Yeah.
that's great. Thank you. Okay, so today's about introduction to learning with computational models. So you will be learning how to use computational models to engage in scientific inquiry. So this CT STEM curricula on this website that we are using, they involve computational models that are designed using using a computational platform, an agent-based modeling language called NetLogo. In this lesson, we will understand what these models are and how to use them. Okay. So this lesson specifically focuses on learning science with these models. And these models are of emergent natural phenomena. So emergent natural phenomena are the ones in which simple interactions between autonomous agents and environment result in complex patterns. For example, a flock of birds. So when you see a flock of birds, uh, it creates a V shape, and not every bird in the flock is aware that it has the flock is flying in the V shape. But because each bird follows simple rules regarding alignment, coherence, and separation, the flock emerges as an emergent pattern. So this is an example. Today we will be looking at a different immersion phenomena. So in this lesson, you will use a NetLogo model about wildfire to learn how to computationally study spread of wildfire. You'll learn scientific inquiry practices and you will engage in computational thinking practices. So we'll focus on data modeling and simulation, computational problem solving, and systems thinking practices. So Asim and Prachi, can you go to the next page? Answering the questions. So I will give you 5 minutes to answer these questions. Okay, great. So while Prachi and Asim are answering these questions, I'm going to talk to you about this lesson. So this lesson is designed so that students can learn about computational modeling. And I'm going to increase, some of you are using your phones, so I'm going to increase my font size so that you can read it clearly. So there are questions on this website, and students can, once they log in, they can use this website to answer these questions. So I'm going to give you a minute to think about this first question. Since this is organized by Royal Chemistry Society, this is a chemistry question. I'm just joking. This was there before this talk was announced. But so those of you who are chemistry teachers, you can have different answers to this question, right? So it only became widely accepted knowledge that all matter in the world is made up of tiny elementary particles. So this was figured out in 19th century. Let's look at the picture below. Can you tell what it is a model of? So some students write it's a model of an atom. Some students write it's a model of a neon atom. Some students write something else. And those who are thinking it's a neon atom, it may not be. It could be an ion of any other element who has lost electrons or gained electrons. So this is just an example of what a static model looks like. And these kind of models are used in science classrooms. But in this case, students think about what is usefulness of these models. And then there is a computational model of wildfire here. So students can, and right now I haven't told Asim and Prachi how to use this model. So they see something like what you are seeing in the classroom, what you are seeing on your screens. And so there is this black square and there are these buttons and there is something that you can move around, something you can change. And if you click on setup, then you see something change in the model. You start seeing these green dots. So this model is a top view of a forest. So this is a model where there is a helicopter or a drone hovering over a forest, and each green dot represents a tree. And they are going to study how wildfire spreads. So let's go back and see what progress they have made so far. Asim and Prachi.
Yes, sir.
Prachi, can you hear me?
Muted,
I
Prachi.
can hear me. Okay, great. So have you finished all the questions on this page yet, or you need more time?
So I have finished till question 1.4.
Okay,
there are two more.
Okay, so I'm going to give you another minute.
Yes.
Yeah,
Yes.
I'm going to give you another minute to finish
Okay.
those two questions. Okay, great. So the later questions on this page ask students about what could be underlying rules in this model. How is spread of fire is modeled here, and then they are asked to make a guess how density of trees affects spread of fire in the forest. And finally, they're asked to think about other factors that they can add. So in this particular model, students are studying correlation between density and spread of fire, but spread of fire could be dependent on several other factors. And students can write about those factors in the next set of questions. So Asim and Prachi?
Yes, Sugat. Answering last question.
Okay, great.
Last
Yeah, and that's okay. Even if you haven't answered the last question, that's fine. You can answer it later. We are going to have a class discussion now.
Okay.
So Prachi, can you share your screen and go to question 1.3 and
Yes.
tell us something interesting that you have observed?
Yes. One 1.3. Can you see my screen now?
Yes, we can see yours.
Yes. So the question is, play with the model and make your observations. Describe what could this model be useful for researchers or other people using it. So my answer to this is this model is useful to study relation between various parameters between density of trees in a forest and spread of wildfire, the percentage of spread of wildfire.
Okay, that's a great answer, Prachi. Can you tell us how you arrived at this answer? What did you do with the model?
So here I was playing with this model. So here you can see the density over here, and you can change the density using this. So let's say I'm putting it at 36, and the model speed is here, but I will soon come to it. Then setup. If I say setup and go. So over here, it tells me that 1.1% is burned. Now, if I increase the density, I tried with, suppose this 71, set up and go. Okay, so this starts, you can see that if this green dots are the trees and the red dots are which tree is catching fire. So then you can see that it is moving ahead slowly. And if I increase the speed over here, the process
Okay,
20.
thank you, Prachi.
Okay, yeah.
Yeah. Okay, Asim, can you share your screen and
I will stop sharing my screen.
tell us your answer to the next question?
Okay. So question 1.4.
Yes.
Okay. So the question was, can you guess a rule that tree might follow in this model regarding catching fire? So immediately what I felt was, to catch fire, I mean, trees must be in close vicinity with each other. And second, I also observed that the fire can come from any direction. It's not just that one tree behind another can catch fire. But if it is surrounded by one or two or three, whatever, 4 trees, one tree is also enough to catch fire.
Okay, that's great. How did you figure
And
it out?
yeah, so by one is changing density. So
Mm-hmm.
at lower density, like Prachi has shown, you can see uh, there are separate patches of
Mm-hmm.
trees, and if I increase the density, I could see slowly the pattern. So if I go to even higher, I can see how this particular red dot is progressing. So this is what
Mm-hmm.
I looked at as fire, and then these are basically looks like pixels, right? Squares.
Mm-hmm.
So if I look at it, the squares are trees, and if they are surrounded, so if the green tree which is yet to catch fire is surrounded by red tree which is on fire, so that gave me an idea. So I cannot increase the size of the tree right now, but this is what my guess is.
Mm-hmm. Great, great, great. Asim, good answer. So,
Thank you.
so we're not going to discuss all the questions. So
Okay.
can both of you move on to the next page and start working on it? I'll
Yes.
give you 5 minutes to work on the questions.
Okay, I'll stop sharing my screen.
Yes, please. Okay. Meanwhile, uh, the audience, let's look at um, the next page in this lesson. So it says a not so sneak peek into code behind this model. Okay. So students can see the code of this model, and that is the computational code. So what it says is here is a model of wildfire that a team of researchers tried to modify, but it does not run as they expected. In fact, it broke. It does not run at all. Can you help them understand this model? And you click on it, and once it loads, you see that instead of green, there are blue patches. And when if you click on this button, go, nothing really happens. So fire doesn't spread. So there is this thing called net logo code here, and students can click on this, and then they can see the code behind the model. And this is a fairly short code, just 36 lines, um, and they can read and understand what's going on. But in this particular case, the first question asks them, set up the model. What's the mistake? Or what computer science people call bug. So computer science coders call this a bug. So students are asked to find the mistake in the model. The mistake is that there are blue dots. So students are asked to click on the blue bar that says net logo code, and then they're asked to fix the error, the bug. So Asim and Prachi are trying to fix that bug now. So first students are asked to identify the bug, then they're asked to fix the bug. Um, so I want you to notice that in this particular case, students are not shown how to do it. They're allowed to explore the model and try things themselves and see what they can do. And I have taught this lesson many times to school children, and I've seen other teachers teach this to school children. And just like Asim and Prachi, even if they're much more uh, knowledgeable than school children can also very effectively solve these questions. And even if one student solves it, they can share it with others and they learn from each other. So the next question on this page is interesting, where students are asked to pick any line of code and explain what it could mean. So students are encouraged to identify different parts, and they can choose. They can choose to pick a very simple line, or they can choose to pick a very difficult line. there is an example which helps them think about this. So these questions help students think and answer certain aspects about the model. So let's get back to Asim and Prachi and see if they have figured out. Okay, Asim and Prachi, have you finished working on the model? Working on
Yes.
this page?
I haven't finished answering, but I think I
Yeah.
know what the issue is with the code.
Okay, okay,
Same here.
that's
I have
great.
answered two questions, but it's there. Like, I've thought about it. Why? Maybe not typed over here, but we can start.
Okay, okay, great. So let's start with Asim this time. So Asim, can you
Okay.
share your screen and show us where the bug is, where the mistake is?
Yes. So here in the NetLogo code, like you have instructed, initially here in the setup section, there was P color given as blue. And that's why I think we were looking at trees as blue. But later, when the program wants to count the trees and fire to go on, the color was given here as green, and also later in the program. So I think that was the issue.
Okay, that's great. So can you change it back to how it was?
Sure.
And can you see if the model runs? Can you click on setup? Okay, this is how it
Yes. So now
was.
setup. This is how it was, and I tried to run, but it couldn't. I tried changing the density also, but it didn't matter. So when I went to next question, where you have asked her to check whether the blue color and green color is not matching. So when I go to NetLogo code, this is what I could see, that initially the density of trees was given as blue color. So I just tried. I like you said, I don't know how to code, but I could see the color given here was different. So I tried changing here as green, and like given I recompile. And then if I try this again, now it is green and it also runs.
Okay, great, great, great. That's wonderful. Did you do the similar thing, Prachi?
Yes, I also did the similar thing. The first, like Asim also mentioned, the first thing which I noticed was the color blue over there, because of which the trees were seen blue, which I changed, and then it started working fine. Also, the number of ticks, like initially when it was blue color, without changing the code, if I say that set and go, then only one tick it was showing, because of the
Okay.
error, because of the error which was there,
Yes.
that the blue color which was written, that was the error. If I change it to green, when I later on change it to green, it was working fine, showing me up to 500 ticks and so on. So
Okay,
that was the bug.
that's wonderful. So both of you figured out the bug and debugged the model.
Great.
That's nice. Okay, so now can you go to the next page and start answering the questions?
Okay. I'll stop sharing my screen again.
Yes, thank you. Okay, I see there somebody in the audience has raised their hand and they have a question, but we will get to audience questions later. So for the audience, the next page in this lesson is about systematically investigating spread of wildfire. So if you remember on page 1, there was a question, what is the relation between density and how much fire spreads, right? So in this case, students are given a research question which says, how does density of trees in a forest affect spread of wildfire? And then there is a hypothesis. So the answer is stated as a hypothesis. As the density of trees in the forest increases, percentage of forest burn will increase linearly. That means if density of tree doubles, percentage of forest burn will also double, right? So I want you to think how will a graph look like? Okay. So if I plot a graph of density, so on the x-axis there is density of trees, and on the y-axis there is percentage burned. And I conduct multiple experiments, right? So in first experiment, I set density to 30%, and I run this experiment and I check how much percentage of forest is burned. Then I change the density. So in first experiment, I set it to 30, and then I check how much is burned, and that gives me 1 point. Then I change it to 50, and I get another point. Then I change it to 70, I get another point, right? And if this relationship is linear, which is what our hypothesis says, the line, I want each of you to think how this relationship will look like. And you don't have to, you don't share your answers, but this is one one possible way look like. Another possible way is that it suddenly increases and then it doesn't. Another way is it doesn't increase initially, but then it suddenly increases. Another way is it doesn't increase, then increases, and then it stops. So there can be multiple ways in which this graph will look like. So here students are asked to collect data. So they're asked to perform experiments by systematically changing this density. So they can start with 35%, and then they can set up. And when they run the model, they get this value here, which is, in this particular case, it's 2.11 after the model has stopped running. And then they can enter this value. Now, there is some kind of randomness that is involved in setting up these computational models. So when you do the experiment again, you're not going to get the exact same value. You'll get similar value, but it's not the exact same. And students, those and why that happens. You can also later on read the code and understand why that happens. So students are asked to create the graph, then describe their observations. Then they're asked if the evidence they have gathered, does it support their hypothesis or not? And then they're asked to explain their answer. And finally, students are asked more questions about their answers. So I'm going to give Prachi and Asim another minute, and then we will see what kind of data they have gathered. Or have you finished already, Prachi and Asim?
I have finished entering the data.
Okay, that's great. So let's compile your data. Okay. So this is what you have done, right? So you have run the model and you have identified some values, right?
Yes, percent burn. Yes.
Percent burn. So initially, so I'm going to do who did 35%. Have both of you?
I can. Yeah.
Okay.
Yes.
I can share my readings.
Okay. So I got 2.05. What was the value that you got, Asim?
So for 35%, I got 2.29 and 2.11.
2.29. Okay, I'm going to enter that.
is
What was that?
it's 2.11.
2.11. Okay, great. For 40%,
Again same 2.29,
2.29,
and second trial is 2.2.
2.2. Okay, great. For 45%,
It is 2.09
2.09,
and 2.11 again.
2.11. For 50%,
For 50% it increased to 3.54,
3.54,
and second trial is 3.92,
3.92. Okay,
and for 55 it's 4.13
4.13,
and 4.78.
4.78. Okay, let's ask Prati also.
Okay.
Prati, can you
Okay.
share your values?
Yes, for 60, I
Mm-hmm.
got the first value was 73.9
73.9. Okay.
and the second was 76.2.
76.2. Okay.
Yes, for 65,
Mm-hmm.
it was 94.64
94.64.
and the second value was 92.4.
92.4.
For 70, first
Mm-hmm.
value was 98.9
98.9.
and second was 98.62.
98.62. Okay.
Yes. For 75, it was 99.8
99.8.
and the second was 99.9.
99.9. Okay, that's fine. So
Yes.
you see this graph here, right? And I'm going to increase my screen size so that audience can see it clearly. This is what we are talking about, this graph. So is it a linear graph?
No.
No.
So should we accept or reject our hypothesis?
Yeah, based on the data, we'll reject our hypothesis.
Because we thought, so whatever that is stated on this page, it says that the hypothesis is that as density increases, the forest burnt will increase linearly, right? So,
Yes,
and our
yes.
evidence, the data that we collected is not supporting that
No.
observation.
Hmm.
No.
Okay, so that, Prachi, you have some question?
No. So it follows a linear pattern, but suddenly after a point, it shoots out. So just
Yes, yes. So over the entire range of the data, it is not consistently linear. So initially you see some small increase, which could be linear,
yes.
but then there is a sudden jump, right? That's very interesting. Thanks for pointing that out, Prachi. So there is some kind of sudden jump here, and that is a property of non-linear complex systems. And there are several such systems around us that can be studied using this kind of computational models. So it's great that you have collected this data and you have understood how the relationship looks like. Okay, so I'm not going to ask you to do fourth page because we have given enough demonstration, but I'm going to tell the audience what the next page is. So on third page, students performed an experiment that was given to them. So there was some kind of a research question, some kind of hypothesis that was given to them, and they performed an experiment. The next page, students are asked to come up with their own research question and hypothesis. So this model is slightly more elaborate. So there is a probability of spread because depending on the dampness of the air and humidity and so on and so forth, the probability of spread could be different. There is something called wind speed. So there is south wind speed and west wind speed. So students can change wind speed. So they can study multiple factors. So they can come up with different hypotheses regarding these factors, and then they can study those. So Yeah, thank you, Asim and Prachi, for being students in this demonstration.
We enjoyed
Uh,
the exercise.
Yeah, really.
Thank you. So let me go back to the slideshow. So we conducted this virtual demo with Hasim and Prachi, and this may have looked like a kind of a staged thing, which was, but but it is possible to do this kind of things with students, and we wanted to show you some highlights. So this curriculum is freely available, and there are a bunch of other curricula that are freely available on this website, CT STEM at Northwestern. So this link will be shared in the in the description, and you can play with these models and look at these questions yourself, and then use it to assign it to your students. So I want to think. I want you to think about how this class was different than a typical science or mathematics or any other class, right? How was it? What was different in this virtual class? What did students do? They were actively learning. They were engaging. They were answering questions. They were doing things. They were engaged with the computational tools themselves. As a teacher, what did the teacher do? I wasn't telling them what to do. I wasn't showing them. I wasn't telling them, okay, this is the procedure. I will first demonstrate, then you do it. No, it wasn't like that. I was asking them to think about these things and then share their answers. And there was some discussion. And this can be more elaborate in a typical class. So how did they interact with each other? Teacher and student, I was asking them questions. They were freely sharing the answers. And this was easy because they are my colleagues. But in other settings, you can create this kind of sharing environment. It will take time. It might take a few days or weeks for students to open up and be comfortable in sharing. But as they start sharing, you can hear about their ideas. You know what they're learning, how they're learning, and they can learn from each other. So this is the website on which you can go. So you can register on this website as a teacher, and then there are a lot of such curricula that are freely available for physics, chemistry, biology, very specific things about evolution or electricity or things like that. And you can use computational models and curricula like this. You can also copy those curricula. So once you create a teacher account, you can copy those curricula and modify those. And I strongly recommend all of you to do that, because then you will be asking your students the kind of questions that you have designed according to their needs, right? So you can maybe simplify the curriculum or maybe make it more difficult depending on student learning level and abilities. There are a couple of other computational thinking in STEM. So in this particular case, we are thinking about computational thinking in the context of science, technology, engineering, mathematics context. So there are two other websites, Concord Consortium and FET, that are developed by University of Colorado and Concord Group. And you can, they have a bunch of free resources like CT STEM that you can use. CT, computational thinking, is taught in two different ways. So CS Pathshala is another rich resource that several educators in India have put together, and they're doing fantastic work. So, but that is not CT in STEM. So computational thinking as people in this field are thinking and more about computational thinking in STEM has a different connotation than computational thinking in general. And computational thinking in general focuses more on coding and so on. And computational thinking in STEM focuses more on models, data collection, scientific inquiry, and so on and so forth. So today I talked about computational thinking in STEM particularly, but if any of you are interested in computational thinking in general, then both of these resources are wonderful. So with that, I will stop and we can have our panel discussion and questions and answers.
Okay. Thank you, Sugat. It was again a pleasure listening to you about computational thinking. And we have received a lot of questions from various teachers. So I'm going to begin with the most popular question that I think most people have asked. And I'm trying to compile as much as possible. But if I forget someone's name, please, forgive me with that. But a question is on the lines of, is it necessary for a learner to know NetLogo coding? Okay, so did Asim and Prachi, for example, had to know what the coding was? And is it important for the teachers also to know NetLogo coding to have this kind of teaching and learning process in class? And this question has been asked by K. Vimla ma'am and Swati ma'am and many other teachers as well. So how important it is for teachers to know coding before they really start practicing this?
My answer is no. It's not necessary at all. Having some kind of understanding can be helpful, but it is not requirement for sure. So Asim and Prachi, they have been working on this project for past few months, and they have some basic understanding of NetLogo, but none of them have formally studied NetLogo. I have not formally studied NetLogo when I started using it. So there is no need to formally know NetLogo to start using these models, not for students, not for teachers. Having said that, NetLogo has been designed to be an educational coding language. And what that means is the structure of the language is such that students can easily read the code and understand. So in this particular case, when the code says asks neighbors set color red, students can see, okay, so neighbors of that particular tree are asked to set color red. Why? What is going on here? Why they're red? Because I'm red. What does that mean? I'm red, that means I'm on fire. So I, as a tree, I'm on fire. So how fire is going to be transferred to my neighbors, right? So students can read and learn about it. Teachers can read and learn about it, and teachers can learn with students. So sometimes students can figure things out earlier than you, and they can share it in the class, and then you can learn from them.
Yeah, that's, I guess, very true with this generation of students, is that they're way faster with technology than teachers. That's what we are observing. Apurva, do you have the next question?
Yes, I am also going to combine. Am I audible?
Yes.
Okay, great. So I'm also going to combine a few questions like Neeraja did. And many people, including Sarabjit Bhasin, Gajanan Sawant on YouTube, and Shanta Krishnan, um, and Moshini Chatterjee. All of these people have asked questions which are related to the age group of the students. So there are questions like, from what age should we use computational models? Can we do this for middle school or high school? for what level of children should we use this kind of teaching and so on. So basically, a lot of people want to know when to start.
Okay, that's another great question, and all these questions are very important. I'm also going to request Prachi and Asim to jump in when you feel contribute to this discussion. So I
Yes.
think some of the research from my research group where I'm working currently, we have worked with students from third standard up to uh, PhD students. Uh, and so for these kind of learning environments, we call them low threshold, high ceiling. So it's easy to participate. And you have seen toddlers in your own house or with your neighbors and so on, that they're fast picking up with the technology. So it's not important that they have to understand all the coding, but even third standard students can click on buttons and make observations and then change things, change the parameters and make different observations and learn what's going on. So for younger students, it will help to scaffold to support their learning more. Um, and then they should be encouraged to be independent learners so that they can reach their own potential. Asim and Prachi, you want to add anything?
Yeah, just I mean on a separate lines, uh, I understand, and me and Prachi who don't know how to do coding, right? But to start with, I think NetLogo itself has lots of models which are ready. So as a teacher, first thinking about the lesson itself or the classroom planning, and to use ready-made models, that can be a beginning. I mean, that can be a starting point. And so this is I'm sharing based on my own experience. So first starting with readily available models, and then going into some details and coding and changing, I think that will help.
Great. So mainly the consensus seems to be that how you design the lesson is more important than what age you start with. You can start and as early as you like. So right from third standard to Prachi and Asim.
Yeah.
So so Prachi, you wanted to add something to?
So just one thing, that while doing all this, students will feel so interested. Like we were also feeling like fun doing. We are learning and then also having fun while doing all this. So that is a major part. So how you will, get students' attention for the concept which you want them to teach. So this would be the, during this current scenario, this would be one of the best things to teach students.
Thanks, Sugat, Prachi, and Asim. So the key takeaway is the right designing of the lesson, and the age is not really as important. Right. Thank you. Neeraja, do you have the next question?
Yes, and indeed, it's about a number again. So, age is just a number. But the other question regarding the number that has come up is how do we really? I would like to know how it can be implemented in a class of 60 students, or if I have much larger classroom population than that, how can I, as a teacher, handle it? And the question is from Sharmishta Patel.
Okay, thank you, Neeraj, and thank you, Sharmishta ji, for asking this question. So I think that is an extremely important we want so many students to learn simultaneously. How can we do that? And what is important is when we want students to uh, uh, in large group to learn about these things, we create some kind of classroom understanding. So let me give you an example from my work in India and in Pune. We worked with bunch of teachers in 5 different schools, and they taught these lessons in classrooms with a class size of 40 to class size of 60. In one case, it were helping each other. So, but that was before COVID, so it wasn't remote learning. But I think for remote learning scenarios, this has additional advantage, that this that students can work on their own. What is important for large class size is to develop some norms about sharing. So I will suggest a few things. One thing is you can ask them to work in groups of 3-4 so they can share it with each other first. And then one of them can share their collective findings with the group. And if you make 10 groups of 5-6 students each in the class, every time you can ask different group to share their findings, so that they get to share it with each other, they get to share with the bigger class and so on. So that way, more number of students can be engaged effectively.
Right. Actually, since you mentioned your work with the school groups here, or schools around Pune, there is one more question which has come up, which is very related to that. So I will ask that one as well. The question is, to conduct computational models in the class, all students need to have access to either laptop or a tablet. But how about schools that do not have a computer for each student, or really economically backward schools which do not have a laptop for each student? So how can we combine learning in that case?
Okay, that's also a very important question, and that is something that I have been working. I mean that is a question that concerns me also a lot, and so there is no simple. So for these kind of tools, you need a computer. So one has to figure out how resources can be mobilized, and so I will give you a non-COVID answer, and then we will think about COVID situation. But maybe in the post-COVID world, um, having a computer lab. So asking all students to be in a computer lab um, in a generative way. So computer lab sessions should not just be come to computer lab. These are the steps. Take this printout. Do this. It shouldn't be like that. But they should be allowed to engage with these models generatively. They have to be active inquirers. So what is done with these models is also important. So a computer lab can be an option. Also, there are some newer platforms which can be used on cell phones, but uh, the one that I'm currently working on, we are developing a new version of NetLogo that can be used on cell phone, but it will take a couple of years, maybe, or sooner, I don't know. But that will also help reach more students faster.
Right. We really hope that you come up with that model sooner than later. Thank you for sharing that. And Apurva, do you have the next question for Sugat?
Yes, I do. Again, it's a combination of a few questions, and they all another aspect, which is subject specific, models and things like that. So some people have asked, can do you have a model for chemistry or geometry or mathematics, or are there any sample or ready computational models for various topics in science, and so on? So which subject
Um,
is suitable for this kind of teaching is what people want.
okay, so good that you asked that question, because there are two aspects of these models. The first aspect is a model itself, and the second aspect is a curriculum that uses that model, right? So So this website CT STEM, and I'm going to put that link again in the Zoom chat for Zoom people, and it will be on the YouTube also. So you can go to this website, and on this website there are many curricula that have already these models integrated in them. So there are questions with NetLogo models, and so you can use both the model and the questions. And you can also copy that curriculum and then change those questions so that you can add your own questions. Some of them may be related to models, some of those may not be related to models. Some of those could be asking students about their own experiences in their neighborhoods, relating the context of the model, and so on and so forth. NetLogo is a modeling software which has a lot of models in its library. So that is an additional thing. So if you go to NetLogo website, so if you just Google NetLogo, you will see NetLogo. It's free. You can download it on your computer. There is a web version that you can use it on computer browser, and that will help you look at several NetLogo models that you can additionally create curricula with, and then use those in your classroom. So there are both these options that are available.
All right, great. Thanks, Sugat. So there is some sort of a library on CT STEM which one can explore. And the idea is to integrate this kind of model building and model exploring activity, and that can be done in any subject pretty much. And I would like to add here that when Sugat worked with school teachers here in Pune last year, the models that were made were from a very diverse range of topics, right? Sugat, from mathematics to physics to biology and so on.
Yes. Yeah, that's yeah. Thank you for reminding about that, because there were several topics like reabsorption in kidneys to free fall of an object to Mendelian inheritance. And all these curricula are available on the CT STEM website. So, and these are some of the CBSE. I saw someone asking about CBSE syllabus. So don't think about changing or this method to teach everything in the year academic year using this method. But even if you do it for one topic, that will give students really good exposure about using these ideas. So even if you spend a week or two, I mean, if you can spend the whole year, that's fantastic. But even if you can spend a week or two of every year engaging students in this kind of thinking, that will be helpful.
Great. Thank you, Sugat. Neeraja, you have the last question, perhaps?
Okay, I have actually 2 or 3 questions, but which are very important questions, so I want to ask them. One which has come from Marathi medium school teachers, or a language, we can just make it for a language other than English. They wish to know that is there any option to choose language while using CT STEM, or are there other websites that are more user friendly with respect to the language, because they're worried that their students might not understand English when they really see the simulation. I know that you worked with some Marathi medium schools here, so I wanted to also ask you, can you share that experience alongside as you answer this question?
Yes. Neeraja, can you ask all, or you have combined the questions?
I have combined 2 or 3, but my last question to you is if I, as a teacher, want to really start working on computational thinking or incorporating computational thinking in my classroom, what should be the first step?
Okay, great. So I will take both these questions one after another. So first question is the language thing, and that also relates to the second question, because as a Marathi medium or as a Tamil medium teacher, what should I do? So you can design questions in your own language, right? So, and it doesn't have to be on the CT STEM website. Those could be in a Google Doc or something somewhere else. I mean, if any of you are interested I'm happy to work with you so that we can customize it and see how we can do it, because it is possible that there are now so even on the CT STEM website you can use Marathi font, but students will not be able to write their answers in that font. So it has to be some kind of innovative solution that there are a set of questions, but students can answer it using pen and paper, take a photo, upload it, or something like that, right? So we can be innovative about it to make sure that students of all backgrounds and all languages can use these tools. NetLogo has been translated, the software has been translated in several languages worldwide. So it's very popular in China and Japan, and it runs totally in Mandarin. So the script and everything is, it hasn't been translated in many Indian local languages. There was an attempt to do it in Hindi, but I don't think it's complete. So right now it's in English, but still a lot of Indian students, even if they're not in English medium school, they know English words. So it's not like a situation in China or somewhere else where they are not familiar with English words at all. So they can see the model and they can read the word and they can read density and they can understand, okay, ghanata. So when you can, they can connect the dots, and there are semi-English schools also. Um, so that is the thing. Second question is CT STEM. So how can one start using these models? So I recommend that you go to the CT STEM website, the link that I shared in the Zoom classroom, and register as a teacher. And once you register as a teacher, so that's the first step. There is a tab called Teacher Support, and there are, if you go through that, there are frequently asked questions which will guide you how to set up your account, how to assign curricula to students, and so on. So all that information is there. And yeah, thank you, Asim, for sharing this in chat. So what I'm going to do, I think some teachers are leaving, but I want to summarize. So I want to share one last slide of summary. So in 1 minute, I'm kind of going to summarize this talk. So we have discussed how effective computational models can be to teach science. When you're using computational models, the most important part is you should use them to facilitate students' active learning. So students should be doing things. They should not just be observing you demonstrating the models. They should be able to play and interact with the models. And that is extremely, extremely important. Any platform that you use, even if it's FET simulations or any other simulations, if you're using in the classroom, try to make sure how students can have access to those models, how they can play with those models themselves. The third point is teachers should facilitate student learning by pointing them in the right direction and not giving answers directly. So even when students are answering these questions on CT STEM website, you should not give them answers directly. You should guide them. You should ask other questions. Okay, you can't figure out how to run the model. Can you ask your friend? Or uh, facilitate peer learning, facilitate by saying, okay, you can look at the model, you can change this particular parameter, see if that has an effect. So don't tell them do this, do this, do this, but just ask them guiding questions. And the last point is extremely important, that struggling and failing are important parts of learning. These kind of learning environments, several students will struggle and will fail. And as a teacher, you will sometimes feel that you are struggling and you are failing. But all of us are learning. And my past 4 or 5 years of learning as a researcher and as a designer, I have struggled and failed a lot of times, and that has been helped me improve my own designing. So this kind of struggling and failing with these curricula will help your own teaching and will help students learning. So with this, I'm going to share my email. So those of you who are interested to stay connected, um, please write to me. I will be happy to help you with any kind of questions that you may have about using these curricula in your classrooms. Um, we are also thinking about creating a WhatsApp group of teachers who are interested in using these models so that you can share your own experiences with each other. And whatever new curricula that you create, others can use it, or you can use curricula that are created by others. So I will be extremely happy to help in the process. So you can write to me, and we will possibly circulate a Google form to sign up for a WhatsApp group, and then we'll create such group, and we'll see how we can figure these things out as a community. Because you have raised a lot of important questions. There are no easy ready-made solutions. How to teach it with 60 students, how to teach it with classes, with regional languages, and so on. So we have to do this together, and we can figure it out together. Thank you.
Thank you so much, Sugat, and I'm really glad that you're ready to help the teachers and work with them such that they can adopt this in their classrooms. So everyone, we will be sharing a Google form with you next week. If you wish to learn more about computational thinking and scientific inquiry, please fill that Google form, and then we'll go ahead with the decisions of how to create the model. And we'll works together to, as Sugat said, to find the answers to these questions. Thank you so much, and it was a great session. You can see a lot of comments, and I will share the chat with you later on. So many people enjoyed the talk, as well as it was very informative and engaging at the same time. So thank you for doing that. Um, so, to everyone, I want to share a kind of a teaser for our next webinar. And this is, if all of you can see my screen, this is a topic that gets talked a lot about, is asking students to do projects. And so next webinar is on project-based learning, and exactly what Akash and Sarita are going to talk about is how can we get students to drive their own learning in a project-based learning approach. Again, these are two teachers who have worked very closely with students across India, and they wish to share their experiences with everyone. So thank you for being with us. Thank you again, Sugat, Asim, Prachi, Apurva, and the whole team, as well as everyone who attended today's session. Thank you for being with us. Thank you.
So, Neeraja, if I can just
Thank you.
add a quick
Yes.
announcement. A few people have been asking about what happens if they, for some reason, are not able to join through Zoom. So, I just wanted to say that this is available, the series videos are available on YouTube on the IISER Pune Science Activity Center YouTube channel. We'll put the link in the chat box. Of course, you may not be able to ask questions and so on. So you may miss that part of the interaction, but you will still be able to see some of the videos in case you have missed.
Right. And one more thing that I wanted to add is that our Zoom the number of seats are not getting filled. So, or they're not completely full. So if you had tried it for the first few webinars and couldn't get a seat, please try it for the next webinar. I'm sure you will be able to find yourself a seat in the Zoom room. As Apurva said, it has the advantages of being able to participate actively in the webinar. So please first log into Zoom. Okay. So thank you for being there with us.